Howdy, howdy, y'all. Welcome back to some more math, where today we're going to be talking about matrices. Matrices are a bit of an odd topic, right? But they really are the gateway to a lot of things that are done in higher level math, especially a lot of really complex functions, say like groups of functions working together. Trying to solve for those is nigh impossible using what we know so far, but pretty easy using matrices. We're not going to get nearly that far into it. We're just going to be going over the real basics of what matrices are and very, very simple operations we can perform with matrices. Nothing more than that. I also will warn they're not terribly intuitive, right? I mean, 2 plus 2. Oh, 4. Okay, it makes sense. That's intuitive. The way that we do math with matrices is less intuitive. But yeah, so just be warned. But without ado, let's get into it. So matrices, right? We're using the slides from McGraw-Hill on matrices, right? What are matrices? Here it is. What are matrices? They are a bunch of things, right? We're going to go over a few things. We're going to talk, well, yeah, on all of this fairly, a fair good amount. Yeah, they can be used in some stuff. We're not going to talk about any of these things, but they are used in solving, like transportation systems, communication networks, tons of stuff. A lot of higher level applied math involve matrices. When you get into things like linear algebra, a lot of stuff involves matrices. So yeah, what's a matrix? Well, simply put, a matrix is a rectangular array of numbers, like a two-dimensional array for those who have done those before, right? Uh, has m rows and n columns, right? That is a matrix, and we have a drawing down here of what a matrix is right here. Basically, I mean, this looks like this thing has two columns, 1, 2, 3 rows. It's a 3 by 2 matrix. Note the square brackets we use around the whole thing. That designates the matrix. And how they talk about equality here? Two matrices are equal if they're the same thing, right? They have to have the same number of rows, same number of columns, and same elements in every row and every column. Pretty straightforward. Here's our notation, right? There's a lot of weird letters and symbols here. But this is showing us about how we denote columns versus rows, right? A lot of times we'll use I and j as our variables here. So what row are we on? The first, second, third, fourth, so on and so forth. What column are we on? First, second, third, fourth, so on and so forth, right? And we'll use something like mj or so like mn, as we see in the bottom corner. Mn is the cornermost, the very bottom rightmost item in the matrix. Hopefully straightforward. You can have matrices which are not one-dimensional, but effectively one-dimensional, right? This thing has a single column. You can have a matrix with a single row, right? Where everything will end up being, I mean, we have J here, right? Let's take a look if we had a one column matrix, right? Um, we would end up with a m by 1 matrix. So let's take a look. I have paint available for us. We just can just draw some matrices, right? Nothing too special to say about them, honestly, right? So matrices can be just arrays of numbers, really. 1, 2, 3, 4. They don't have to be whole numbers. I'm sure you can have matrices of things other than numbers, probably. I'm sure theoretically it's defined that there is a way you can have matrices that don't involve numbers of any way, shape, or form. But that's not pertinent for our understanding of them whatsoever. All right, so how big is this matrix? This is a 2 by 2 matrix, right? What about if we have a matrix like this? 1, 2, 3. Well, let's see. What do our things say here, right? This tells us that we have m rows, 1 column. Rows, columns. So this would be 3 rows, 1 column. That's always the order. And then if we have something like this, well, not like that. There we go. Now I'm not going to get into the weird screens back and forth as much. I should not put commas here. I'm putting the commas anyway. This is going to be a 1 by 3 matrix. 1 row, 3 columns. Pretty straightforward. So that's kind of just a precursor for understanding more on that, right? We can do some math with matrices. We can do addition. There's a lot of words on here on the screen that's go into greater detail. The thing behind me says, note, matrices of different sizes cannot be added. All these words on the screen, what do they actually mean? Well, if we take 2 matrices, say I'm going to make a new layer here for us. We take 2 matrices. We'll say 1, 2, 3, 4. And another matrix, which is 0, 1, -3, 7. We can add them together. How do we add them together? Well, we take each matching index, right? The thing in the first row and the first column of the first matrix will be added to the thing of the first row and the first column of the second matrix to get the thing in the first row and the first column of the sum matrix. 1 plus 0 is 1. 2 plus 1 is 3. 3 plus -3 is 0. 4 plus 7 is 13. My math is wrong on that last one. It's not 13. Math's hard. Is 11. This is what we're left with. That's the sum. Because of that, we encounter issues if we're trying to, let's say we want to add some other matrices, right? 1, 2, 3, and we want to add to this matrix here 0, 6. Well, what will that get us? Okay, 1, so first row, first column, there's only 1 row. I mean, only 1 column. First row, first column, first row, first column, 1. First row, second column, sorry, first column, second row, first column, second row gives us 8. Third row, first column, oh, there's nothing here. Do we put a 0 here? Do we put a, no. You just can't add it, right? It's not accessible. Think about this, the way that I think about this is arrays from programming, right? If you have 2 different arrays, what happens if you try to access an element in an array that is 2 elements large, and you're trying to access the third item? Well, depending on what programming language you're using, it might crash, it might give you a warning. Whatever the case is, you should not do math there. It's not going to be 0. It's going to cause problems in your program, most likely, if you try to access whatever's here, right? So we just can't. These cannot be added together, is the answer. They have to be the same size to be added together. The adding's pretty straightforward as far as matrices go, right? Multiplication is less straightforward. I couldn't read these words, but you can also read these words. The thing behind me says the product of 2 matrices is undefined when the number of columns in the first matrix is not the same as the number of rows in the second matrix. What is that saying? It needs to be a very specific configuration for you to be able to multiply. Specifically, for you to be able to multiply, the number of columns of the first matrix, 1, 2, 3, must be equal to the number of rows in the second matrix, 1, 2, 3. And it's for this reason. A lot of words here and math, right? I think it's easier to understand by example. So let's take a look. Let's try to do some multiplication. We'll start with our simple 2D array, two matrices again. 1, 2, 3, 4. And now let's multiply that by, what did I have last time? 0, 1, negative 3, 7. 0, 1, negative 3, 7. So the first thing we do before we even try to multiply, does this thing have the same number of columns as this does rows? 1, 2, right? 1, 2, and this has 1, 2. So we're good. We can do multiplication. So we can just start multiplying. How do we multiply? Gets a bit weird here. We will decide, the way that I like to multiply is I first want to know how big is the resulting matrix going to be, just so I have it in my planning. To know how big the resulting matrix will be, you take into account how many rows the first matrix has. We'll change it to this color. How many rows the first matrix has, and how many columns the second matrix has. It has 2 rows and 2 columns. So the resulting matrix is going to be 2 by 2. It'll have the same number of rows as the first, same number of columns as the second. So everything matters. You need the row and column, rows of the first, columns of the first and rows of the second need to be the same, and the dimensions of the resulting matrix will be whatever is left. The rows of the first and the columns of the second, 2 by 2. So we're going to have our 2 by 2 matrix. I'm going to make it look wide, and I'll show you why. So now we get into the actual math involved. The math of this is a bit odd. Choose what area we're trying to solve for. We're going to start with the first row, first column. To do so, we will multiply the first row. I'm going to do this in different colors every time. The first row of the first matrix by the first column of the second matrix, because I'm trying to get the first row, first column. How do I multiply rectangles? Yeah, this gets weird. We take the first item in each of these lines. 1 times 0 equals, so 1 times 0 plus the second item of each of these. 2 times negative 3 plus 2 times negative 3. We find that sum, we get our answer. All right, and we'll sure, I'll put the shorthand one right down here. We'll just solve it right away. Bit easier for us this way. So that's 0 plus negative 3 is negative 6. The first index 1, 1 of the new matrix is negative 6. Let's try this with another number. Let's say we'll use green for this one. Now I want to get the thing in the first row, second column. What do I multiply together? The first row of the first thing times the second column of the second thing. First row, second column. Same thing, 1 times 1 plus 2 times 7. 2 times 7, right? First thing times the first thing plus second thing times the second thing. And if this was 20 elements long, it will be then plus the third times the third, fourth times the fourth, fifth times the fifth, so on and so forth until we get to 20. And then 1 times 1 is 1, plus 2 times 7 is 14, gives us 15. Let's go on to another one. Now I want to get the thing in the second row, first column. So I multiply the second row with the first column. 3 times 0 is 0, plus 4 times negative 3. First item times first, plus second item times second. 3 times negative, sorry, 4 times negative 3. What does that get us? 0 plus negative 12. Negative 12. Last but not least, I got to get the second column, second row. Or second row, second column. So I multiply the second row times the second column. 3 times 1 plus 4 times 7 is 3 plus 28. Gives us 31. This is our resulting matrix. This is the product. We can repeat that for other matrices, right? Now let's try to do this with matrices that might look a little bit odd. Maybe we'll do that with, what about this matrix? 1, negative 1, 3 times 2, 4, negative 3. All right. Well, first thing we check. Does this have the same number of columns as this has number of rows? Yes, it does. Right? We have 1 column, 1 row. So multiplication can work. How big is our resulting matrix going to be? Let's actually, I'm going to redo this second matrix just to kind of prove a point. We'll make it larger, right? I'd say it'd give us more math, but it really won't. It's really not gonna matter very much. Does this work? Let's find out. I think I wired my mouse to have an eraser. Yes, I did. We'll put a 1 there, sure. So how many rows do we have here? Well, we have 1, 2, 3, 1, 2, 3, 4. So our resulting matrix is going to be 3 by 4. So let's start on that. 3 rows by 4 columns. Okay, so now what do? We multiply the first row. I want to get the thing in first row, first column. So I multiply the first row by the first column. There's only one thing in the first row and only one thing in the first column, so that's fine. 1 times 2 is 2. We don't add anything, that's it. Because it's only one, this only has 1 row. We don't have to go to the second, third, so on and so forth. I want to now get, let's jump to the opposite extreme. I want to get the thing in the fourth column. So third row, fourth column. I multiply the thing in the third row and the fourth column. Right? 3 times 1 is 3. I can go through and repeat this process for the entire array. First row, let's say I want to print everything in the first row. So first row times 2 times 4 times negative 3 times 1. That gives us the first row. Second row, 1 times negative 2. Sorry, negative 1 times 2, negative 1 times 4, negative 1 times negative 3, negative 1 times 1. 3 times 2, 3 times 4 is 12. 3 times negative 3, negative 9, and positive 3 at the end. That's our resulting matrix. Why didn't I have to add anything this time? Remember, I only had to add things here because I had multiple rows that I had to go through here, right? I had to multiply this times this plus the second row times the second row. The second row times the second column. Here there's only 1 row, and here there's only 1 column, so I don't got to do more than that. Right? And so we got that working. Let's try one more. Let's try this matrix here. I want to multiply 1, 5, 13, 0, 1, 6 times 1, 5, 3, 1, 6, 3. All right, before we start multiplying, do we have the same number of columns here as we have rows here? No, we do not. We cannot multiply. Let's try it, right? Let's say we wanted to do it anyway. What would our resulting size be? Well, it would be the same number of rows as this one, and the same number of columns as this one, so 2 by 3. So let's humor it. Let's try our best and pretend this is going to work. It shouldn't, but we'll see why. So we multiply the first row. We want to get the first item, right? I'll multiply the first row times the first column. So that means 1 times 1 is 1 plus 5, because first item, right? Second item times second item is 5. Third item times, it's undefined. There is no third item. So plus, right, we can't do it. We already have, it's undefined. It's not solvable. We cannot find the product for it. So this is how we can show definitively, even if we try to start multiplying, we're going to end up with problems here. All right, and that's what matrix multiplication is. Here's a picture. I don't think this picture helps, but it's here. All right, I'll move out the way so you can see this formula that will help you potentially. All right, so let's go on and see what else we have. It's not commutative. Why not? Well, I mean, normal matrix normal math is commutative, right? Normal multiplication is commutative. We can see their responses here. AB, BA. These are two different values. The matrices are not identical. So, okay, but that seems a bit odd. Everything else what is identical. Well, let's try it. Let's take a look as to why it might not be commutative. All right. What I'm going to look at is going back to this page. Remember the one we solved right here? Oh, that's what happened. Remember what we solved right here, this thing right here. What if I switch it around? What if instead I tried to solve for 2, 4, -3, 1 times 1, -1, 3? What if I try to solve for that? Well, what's the first thing we got to do? Does the number of columns here, 1, 2, 3, 4, equal the number of rows here? 1, 2, 3. No, it doesn't. So can we do multiplication? No, we can't. So this one we can't even multiply, period. So there's no way the result is going to be equal to something that we can multiply. Like, this is undefined, right? Undefined. Perfect handwriting. This one, on the other hand, is like, what can we do with it? Right? This is an actual matrix. This is undefined. Clearly, they're not equal. So this kind of reinforces that fact that multiplication is not commutative. Right? Yeah. There is a very useful matrix to know about. It's called the identity matrix. Right? And the identity matrix is, I wonder if I could get this to move over. I don't know. I'll just move over for now. The identity matrix is this. There's a long, real weird math about this. They throw delta in here, or a bomb if you're creative, and it's equals 0. That's all to say that for every place where the index of the column and the row is the same, it's set to 1. Everything else is 0. So 1, 1 is 1. 2, 2 is 2. 3, 3 is, sorry, 2, 2 is 1. 3, 3 is 1. 4, 4 is 1. 5, 5 is 1. Everything else is 0. Simple terms, straight down the diagonal. They must be square. All right? It must be a square matrix. Well, no, actually, I take that back. Well, I don't know. We can get into some weird things there. I don't want to definitively say anything. Normally, we will be dealing with square identity matrices. I can say that much with certainty. So how does an identity matrix work? Well, let's give it a shot. An identity matrix is effectively a matrix that holds true for the multiplication identity rule. What's that in math? What's that in normal math? 5 times 1 equals 5. 8 times 1 equals 5. It's basically the 1 of matrices. And we can take a quick look at that and kind of confirm that by doing an example of some multiplication. All right, let's give it a shot. We'll do 1, 2, 3, 4, 5, 6. Well, let's try this. Let's find out whether or not we can have non-square identity matrices at the same time. This will help reinforce things. Right? Because the index of the row and column has to be the same. Well, first off, that multiplication won't work, but I'll find one that does. This one will. 1, 0, 0, 0, 1, 0. Row 1, column 1. Row 2, column 2. Row 3, there is no column 3. There is no 1 to put in there. Let's try the multiplication out. Let's see if it works. First off, are the number of columns here equal to the number of rows here? Yes. What's our resulting matrix size going to be? Our resulting matrix is going to be 2 rows by, 2 columns. Let's do it. Equals this 2 by 2 matrix. Let's get the thing in the first row. I'm actually going to put the equal sign down here. Equals, just so I have space. Let's start with our multiplication. 1 times first row. All right, I'm trying to get the thing in the first row times the first column. It doesn't even need to be that big, honestly. We'll keep it back up here. We'll see why it doesn't need to be very big. First row times the first column. 1 times 1 is 1. Plus 2 times 0, 0. Plus 3 times 0, 0. So our first thing is 1. First row, second column. 1 times 0 is 0. 2 times 1 is 2. 3 times 0 is 0. Okay. We've gotten first row done. We can do second row. Second row, first column. Second row, first column. All right. 4 times 1 is 4. 5 times 0 is 0. 6 times 0 is 0. 4 plus 0 plus 0 is 4. Great. Last thing, 4 times 5, second row, second column. 4 times 0 is 0. 5 times 1 is 5. 6 times 0 is 0. This is our result. So the first question is this, the commutative law says that an identity matrix should give us the exact same result back. Is this the same result? No, right? This does not give us the same result that we had before. Because, well, first off, the dimensions are different, right? This matrix is 2 by 2. This matrix, on the other hand, is 2 by 3. So it's not the same. But the elements that are in it are identical to their mapping. So it's kind of right. Let's try this with something that isn't let's try this with an actually square matrix. We'll keep it simple. 0, 3, 1, 2 times the identity matrix. Can we multiply? Yes. If their square matrices are the same, we don't even have to do the math for that. Let's try it. First row, first column, 0 times 1 is 0, plus 3 times 0. Next, first row times the second column. 0 times 0 is 0, plus 3 times 1 is 3. Next, second row, first column. 1 times 1 is 1, 2 times 0 is 0. Finally, second row, second column. 1 times 0 is 0, plus 2 times 1 is 2. This is our resulting matrix with 2 different colors for the edges. That's going to bother me for no reason. Is this the same as the original? Yes. 0, 0, 3, 3, 1, 1, 2, 2. These are equivalent. These matrices are equal to one another, thus showing the identity matrix is true. Now think about it. What would be the equivalent of an identity matrix? It wouldn't be called that for addition, right? What type of matrix could we use to take, let's say same thing, 0, 3, 1, 2, plus something. We know it has to be the same size, otherwise addition won't work. So 2 by 2 equals, result also 2 by 2, equals 0, 3, 1, 2. This might be very intuitive, but just in case it's not, let's do the reverse of addition. 0 minus 0 is 0. 3 minus 3 is 0. 2 minus 2 is 0. 1 minus 1 is 0. Does this make sense? 0 plus 0 is 0. 3 plus 0 is 3. 1 plus 0 is 1. 2 plus 0 is 2, right? I believe this is called a zero matrix. I could be wrong on that, so don't quote me on that, but I believe this is called just as simply called a zero matrix. And yeah, that's just worth noting. Boom. Oh yeah, we have powers of matrices too. Square matrices can be multiplied by themselves multiple times. A square matrix does times another square matrix of the same size will result in a square matrix of the same size. Remember, it's 2 by 2, yeah, that works. It'll have then 2 rows and 2 columns, just like the original. N by n will result in a matrix that has n by n columns if multiplied by a matrix of the same size. So we're good. We can keep doing that multiplication as we want. Of the same matrix, let's say we have a matrix called A, we can multiply that by itself once, twice, 3 times, 4 times, whatever. Only thing worth noting is, much like in normal multiplication, let's just to hammer it home more than anything. Much like in normal multiplication, oh, well, first let's make a matrix. We'll call it B, and we'll say it's 0, 1, 2, negative 3. In normal multiplication, we'll have something we'll call lowercase b equals whatever, 3. 3 to the 0 equals, or b, lowercase b to the 0 equals what? For all numbers other than 0, because that one gets disputed, that will equal 1. Which is the identity number for multiplication. That holds for that identity real multiplication. Same idea, b to the 0 will equal the identity matrix. 1, 0, 0, 1. For the same reasoning. B to the first is just b. B to the second is b times itself. B to the third is that times it's times b. Fourth, fifth, so on and so forth. Transposes. Transposes are kind of straightforward. There's a lot of words. I think they have 2 pages where they talk about. Oh, yeah, that's symmetric stuff. Yeah, transposes a lot of words to basically say that if you take the thing in the first row, first column, or the m row and the n column of of a matrix, and you instead put it in the m column and the n row of a new matrix, it's called the transpose. That's fancy way of saying, all right, well, we got this thing here goes there. We kind of just flip it like like this way is kind of the flip that's going on. It should be, I would just even just look at this and it should kind of come to you like, all right, this goes there, that goes there. Okay, we just, all we're doing is my camera gonna be wrong here? I think the camera, nope, camera is, yes, camera is wrong. So it would have to be this. This is my drawing hand. I don't have a, there isn't a void particle missing from my from the thing. I promise you. There it is. That's what the transpose looks like. Boop. I don't know if this visual trick's helping. I hope it is. But yeah, that's a transpose. If you have a square matrix is symmetrical if the transpose is equal to itself. Right? What does that mean in like normal people talk? Well, I mean, that is kind of normal people talk. You make the transpose if it looks the same, it's symmetric. How's a quick look? I'll be honest, I'll do this even for matrices up to like 10 rows and columns, just because at that point I'm like, it's easier than finding the transpose. Look down the diagonal, the main diagonal where you have all those ones for an identity matrix. Look down there. Is everything on both sides of the diagonal equal? So the diagonal is the diagonal. 1, 1, 0, 0, 1, 1. Okay, that's equal. Right? If we take a look at another item here, let me make a different matrix. I'm not going to even promise you whether or not this is going to be symmetric. I'm just going to write stuff down and hope it's kind of close, and we'll see whether or not it's symmetrical. Yeah, I like this. And then let's see. Is this symmetrical? Well, we could do a transpose of it, right? We could write out a whole transpose. Okay, 1 goes into 1. This 2 flips down here. This 3 flips down here. This 4 flips down here. This 2 flips up. This 3 flips up. This 4 flips up. All right? We could do this and continue onwards. That's the most effective way. Now we go. The diagonal is always the same in a transpose, so we don't have to worry about those. This 5 will go up here. This 5 will go down here. This 3 will go down here. Uh-oh. You can already see that -3 goes into a different number. That's already a bad sign. This -2 goes up here. -2 goes down here. -3 goes up here. Are these the same? No, they are not. These are not symmetrical because of these things here. So this matrix is not a symmetrical matrix. You can make the whole transpose, or if you can see even just a single value that you're like, let's go down the main, go down the main diagonal here, see if, good. These are not the same. It's not symmetrical. That's how I do it, genuinely. All right, if I'm uncertain, if I need a double check, I'm like, then do a transpose. But if you can find it early on, if you're sure of yourself early on, don't worry about it. 0, 1 matrices. 0, 1 matrix is a matrix that has only zeros and ones in it. Why might that be useful? Well, think about truth tables or anything computer science. What are the numbers that computers know? Only two things, zeros and ones. This is how a lot of computer algorithms work, is using 0-1 matrices. Makes things way faster and way more efficient than if we were just using normal math, right? And we can use Boolean operations on 0-1 matrices. You can have a 0-1, like a matrix that only has zeros and ones, and then add it to another matrix that only has zeros and ones, just normal addition, and then you might end up with a matrix that has twos in it. So at that point, you're not doing Boolean operations, but you can do Boolean operations on a 0-1 matrix, which just is standard truth things. Or, ands, right? They have the words here. The join is basically doing an or on a 0-1 matrix. The meet is the and. Join, so we have a lot of words for it right now. We have join, we have union, we have or, we have disjunction. These are all different words we'll use to refer to the same action, just in different contexts. And then the meet is the same as the and, is the same as the conjunction, is the same as the intersection. Do they have an example here? Yeah, they have an example, kind of. No, this example's good. I don't even think I need to write anything down. The thing behind me is an A. This is the join and meet. We take the things in the two matrices, and much like normal addition, the only difference is instead of doing addition, we're just doing the operation. So 1 or 0. What's the result of 1 or 0? AKA true or false. That's true. What's true? What's false or true? What's a 0 or 1? 1. What's 1 or 0? 1. What's 0 or 1? 1. What's 1 or 1? 1. What's 0 or 0? 0. False or false. And then the same thing for the meet. You're just doing conjunction in this time. So they both have to be 1s for the result to be 1, which is why we only have it down here. I want to say any questions, but I don't think anyone can ask me questions. If I hear yes from my hallway, I'll be quite concerned. This is straightforward. That's just addition, but using Boolean arithmetic instead of decimal arithmetic, what we normally use. But then we have the Boolean product, which is straightforward enough that I don't necessarily want to go into detail and show so many examples. There's a lot of symbols on the screen. Don't get worried. Big things to note. The symbol, the circle with a dot in it, that's a symbol for Boolean product. You need 0-1 matrices. How do you do it? Don't get too hung up on it. It's the same rules that you have for normal multiplication for matrices. The same rows and columns, the same how the resulting size, everything's the same. But you know how you would do the first row, the first item of the first row plus times the first item of the first row plus the first item of the second row times the second item of the first row, so on and so forth, right? Only difference is we do and or. So anytime you would do addition in normal multiplication for matrices, anytime you do addition, instead you do or, a disjunction. Anytime you do multiplication, you instead do an and. That's it. That's the only change. All right. Don't get too hung up on it. It's just that. So they show given A and B, all right, where A is this. Normally, if we were to do normal multiplication, we would do 1 times, we would do 1 times 1 plus 0 times 0 to get first row, first column. And then second row, first column would be 0 times 1 plus 1 times 0. Only difference is here we're doing and or. So instead we do 1 and 1 or 0 and 0. 0 and 1, or 1 and 0. I think I said 0 or 0. The last one, it should have been 0 and 0. Right? That's it. Just replace the addition with or, replace the multiplication with and. That's all you do. Same as this. If you understand normal matrix multiplication, you'll understand you'll understand Boolean product. By understand, I mean memorize. Knowing why it works is not as trivial. And then Boolean power is the same thing. You can do multiplication multiple times, and it's the same thing, right? Boolean power is the same thing as a power of a normal matrix. Has to be a square matrix. Must be 0, 1 for the Boolean power to work. Main difference is, note the square brackets. We use, where's my symbol? Here, my finger. I can't. There. The square brackets in the R to denote Boolean product. That's the really main difference, right? Because if we have our power matrix, they just use no square bracket. Here, for Boolean product, you use a square use a square bracket around the power that you're raising it to. Rules of it are the same as what you would expect. It's the same thing as just doing the Boolean product R number of times on itself. And then they do math. It's kind of straightforward. What you can see, though, as I show here, is if you do in some cases, many cases, if you do a Boolean power enough times, you may end up with a matrix of all ones. And a matrix of all ones times a matrix of all ones is gonna be a matrix of all ones. All right, so then it'll just continue on from there. That's really all I have for matrices. All right. Hopefully, this was a helpful look at matrices. If you want, you can stay around. That's all we need to go for. We'll do a couple more examples of some math, but in terms of material taught, that's it. Let's do a couple more examples before we wrap up the video. Let's take a look at some, maybe a more complex, maybe a large, well, yeah, I like this idea. How about we do a multiplication on a matrix that is this big? Yes. No, I don't want it. I want this. We'll do a multiplication on a matrix that is 1, 2, 6, 7, 3, 5, -2, 0, times a matrix which is this big. 3, 4, 2, 0, -1, -2, -3, -4. First things first, can we do the multiplication on these two? Do we have as many rows in the first? Sorry, columns in the first as rows in the second? 1, 2, 3, 4. Yes, we do. So our resulting matrix, I'm going to do it in like a weird off yellow. That's disgusting. Yucky yellow. That's what we're going to use. The resulting size is going to be 2 rows by 2 columns. So we know our result's going to look like this. 2 by 2. Let's do the long form of it, because we're going to have a lot more math involved in it this time around. So let's multiply. Words are hard. Let's multiply the items of I want to get the thing in the first row, first column. So I multiply this whole first row times this whole first column. What do we do here? 1 times 3 is 3, plus 2 times 4 is 8, plus 6 times 2 is 12, plus 7 times 0 is 0. We can then just do addition. 3, 8, 12, 0 gives us, oh, I don't know. Math's hard. 23. Let's go on to another one. Let's do the second column, first row. We do the first row times the second column. 1 times -1 is -1, plus 2 times -2 is -4, plus 6 times -3 is -18. Yeah, I know, I need to put parentheses around things. Yucky, yucky. Plus 7 times -4 is -28. Which gives us, I mean, these are all negatives, so I can just basically pretend they're positive and then throw a negative sign at the end. 30. Don't listen to the way that I do math. Oh, wait, this is easy. We can distribute that. So 51. -51. Next up. Ooh, this is a cool color. Second row, first column. Second row, first column. 3 times 3 is 9, plus 5 times 4 is 20, plus -2 times 2 is 4. Oops, not 4. -4, plus 0 times 0 is 0. What's the math for that? Well, we end up with 29 minus 4 is 25. And last but not least, we can do, brown. Because there's certain colors kind of like brown. So like a weird grayish color. Yeah, what about that? I don't think we have a color like, yeah, just like a tan. Second row times the second column goes into second row, second column. 3 times, remember, first item times the first item is -3. Plus second item times second item. 5 times -2 is -10. Plus third times third. -2 times -3 is +6. 0 times -4 is 0. That gives us an overall thing of -10 plus 3 is -7. That's our resulting product matrix from these two. What if I should have taken a, why, we can still do it. Take a screenshot. I'm gonna undo all this stuff. Here. Oh, you know what I'll do? I will actually copy our result. This. Let's undo everything for a reason. We're gonna now do the reverse. We're gonna show once again that the commutative property does not hold. But this time we'll actually be able to get a product. It just won't be the same product. All right, I think there's slight flickering going on in this grid. I hope it's not causing anyone any distress. Actually, I kind of like that approach. Let's paste this here. Lovely. Get rid of that. Let's switch it up. Let us instead take this matrix and multiply it by this matrix. This times, I hear what you're saying. Professor, aren't there better ways to do this other than weird highlight and copying and pasting things? Yeah. And your point is, that's too late. Can we do the math for this? Well, let's check. Do we have the same number of rows as columns? We have columns as rows. 1, 2, 1, 2. Yes, we can. Our resulting matrix will be 4 columns, 4 rows by 4 columns. 4 rows by 4 columns. Now let's do the math for it. With my really wonky sides. First row, I'm not going to have enough colors for this, so you'll just have to trust me. We're going to do everything in this pink. Yeah, this pink shows up. This is a nice pink. First row times first column. 3 times 1 is 3. Plus -1 times -3 is -3. First row, second column. 3 times -1 is... Sorry, 3 times 2 is 6. Plus -1 times 5 is -5. 3 times 6 is 18. Plus -1 times -2 is... I almost put 3. 3 times 7 is 21. Plus -1 times 0 is 0. Our resulting values we get for the first row is 0, 1, 20, 21. Let's go on. Second row times first column gives us 4 times 1 plus -2 times 3 is -6. Second column, 4 times 2 is 8 plus -2 times 5 is -10. Third column, 4 times 6 is 24 plus -2 times -2 is 4 plus, you can see, very redundant stuff here, 28 plus 0. What's our final numbers? -2, -2, 28, 28. We can repeat that. All right, and we will repeat that. All right, not terribly exciting. I would try to, the thing is, it takes 100% of my brain power to remember rows and columns for some reason. It's like my left and right. I don't do left and right very well, so this is why I'm a bit worried to talk through it, because I'm concerned I'll make some very obvious mistake, and everyone will laugh at me, and then I'll never live it down, and then I'll probably cry for the next 13 days straight. That would seem reasonable. 12 plus +6, and then 14 plus 0 gives us 7, -11, 18, and no, this is -7. There it is. 18 and 14. And you might see some patterns here with our Boolean product as well as we're going through. Right? If you don't yet, we'll go through it at the very end and it'll be more apparent. 0 and 1, 0 plus -4 and 3 is -12. This yellow does not show up. We won't do yellow. That yellow's, I do not know with compression what's going to happen to that yellow. I don't think it's going to survive. We'll do the same thing, but in purple. 0 plus -12. 0 plus 2. There's so many scribbles on these numbers. 0 plus 2 is a 0 times... I mean, we can already see this is going to be 0 every time. So the first number we're going to be adding is always going to be 0. 0 times 2, 0 times 6, 0 times... It doesn't matter. So I'm just going to look at the last one. That'll speed things up. -20. 0 plus 8. 0 plus 0. Our overall result is negative 12, negative 20, 8, and 0. Question we have is, do we see any patterns possibly going on here? Well, I see a couple of patterns. Let's do it in a light gray. No, we'll use black. Well, there's actually no black here. I see a couple of patterns going on. What's the difference between these two? 1. What's the difference between these two? 1. Same difference. What's the difference between these two? 0. What's the difference between these two? 0. Difference between these two? 4. Difference between these two? 4. Alright, if we wanted to, we could say negative 4, sure. Difference between these two? Negative 8. Difference between these two? Negative 8. This is a pattern that we kind of see emerging here. Where does this come from? Right? We have 1, 0, negative 4, negative 8. But that's not any of our numbers we have here. Right? This is kind of interesting. What could be causing it? And I thought I knew it, but then I saw one thing that threw my math off. Now I'm wondering if I got the wrong answers here. Like, it's entirely possible I wrote some wrong numbers on here. But it's interesting. We're seeing that there's some patterns that could be emerging here. All right, maybe there's some patterns going in the y-axis. I don't know for certain, but I'm going to see if there's some patterns that we can recognize real fast. 8 and 8. No, that looks kind of like it differs a fair amount. Yeah, not so much patterns here. But this is interesting. We're seeing some patterns emerge. What might be causing it? I'm sure if we get more, if we were to go deeper into matrices, we would discover why some of these patterns emerge. And thus some of the key parts about matrices and how they work overall. But for right now, it's just not something kind of interesting to recognize. I didn't want to delete that. Oh, I didn't. Let's do one more. One more example. We'll do Boolean matrices this time. Let's do a simple Boolean matrix of... sure, we'll do 2, 3, 4, 5. Oh, that's not a Boolean matrix. So I'm just like, let's do a Boolean matrix. Immediately throws in things that aren't Booleans. Right? Thinking's hard. I don't know how you guys do it so long. Times. Well, I didn't want to do that. Why did I do it this way? This is not what I wanted to do at all. 1, 1, 1. There we go. I prefer this matrix here. And why am I doing it this way? Wish I could answer that question. Got it. 1, 0, 1, 1, 1, 0, 0, 0. Sure. This looks like a fun thing to multiply. Let's do some Boolean matrix. What's the first mistake I've made? This symbol. If you see this symbol, well, we're just doing addition at that. We're just doing normal multiplication, which will give us a different result potentially. I don't want to do that. So instead, let me change that to the correct symbol. Correct symbol is this. What is going to be the result of this? Well, what's our dimensions going to be? We just follow normal multiplication rules. Our resulting dimensions will be 2 rows by 4 columns. Apparently. I feel like I'm wrong in what I just said. But no, I'm confident. Confidence is key. Let's go on and try to do it. Let's do the long form one of it down here. We'll do like that. first row times the... Oh, I don't want to do this one. It's too late. I already drew it. I just feel like this one's going to be really boring. Yeah, no, we're redoing it. I'm scratching this whole idea. See, I was off to the right idea initially, and then I butchered it by putting it in the wrong direction. 1, 0, 0, 0. That's what we want. This is what I want to do multiplication of. Times this matrix. 1, 1, 1, 0. What does this equal? There we go. I like that a lot more. I don't know why I said I'd like that a lot more. I've just lied to you again. Whatever. It's too late. I'm too tired. Let's see. Can we do the multiplication on it first? Yes, we can. Right? We have the same number of columns as rows here. Resulting thing is going to be the same number of rows as columns. Doesn't matter. We get practice drawing matrices, I guess. Let's do the math for how it's going to be. I think this is the first one we've done a tall matrix anyway. That's the official name for these matrices. It's not. I'm calling them as a tall matrix. Let's try to do the math. First row, I want to get the thing in the first row, first column. First row times the first column is 0 and, instead of times, and 1 is 0. Or 1 and 0 is 0. Resulting thing is 0. Next, second column. 0 and 1 is 0. 1 and 1 is 1. 1. 1 and 1 is... Sorry, yeah, 1 and 1 is 1. Or, well, we can do a shortcut for this one. I'm going to change color. We can do a shortcut for this one. Not much of a shortcut in this case, but it's worth noting. 1 and 1 was 1. What do we know about our rules? Specifically, what do we know about how OR works? Everything past this is going to be a disjunction with something else, right? And what do we know about disjunctions? If one thing is true, the whole thing is true. So if we had 1,000 terms here, and we have one of them that's true, so true and, or it's a true or, B or C or D or E or F or G or X or whatever, the resulting thing is true. So I don't have to do the rest. Or whatever, I don't care. We're good. We can just skip. Next, this column. 1 and 1 is 1. I can skip doing this, 1 or 1, if I wanted to, right? And I do. Let's skip it. 1 or 1 gives us 1. 1 and. 1 and 1 gives us 1. Doesn't matter. Everything else is OR. Who cares? 1, then we have 1 and 1. Once again, gives us 1. Last thing, 0 or 0 or 0, and 0, 0. What do I already know is going to happen here? Well, I have 2 zeros side by side, right? If I have 2 zeros that I'm going to be multiplying, it's going to be this and something. That's going to end up being 0. Doesn't matter what the other thing is. Or this and something. That's going to end up being 0. Doesn't matter. So I already know automatically the bottom row is going to have 2 zeros in it. Right? Because no matter what we multiply, let's make it, if we have it really large, right? This is going to be a obtuse drawing, but that's fine, right? 0, 0, 0, 0, 0, 0, 1, 2, no 2. 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0. If I start doing multiplication in this manner, what do I already know? Well, let's say I multiply this whole row with something else. They're all zeros. So it's going to be this 0 times, 0 and whatever, 0 and P equals 0 by the domination laws. So that's going to be false or 0. We know the result is going to be 0 or 0, still 0, or 0, still 0. The whole thing's going to end up being a 0. So we know that the resulting of the new matrix that we're getting, that new row is going to be all zeros. And that's what I've just done down here. We shortcutted a few things. That's a cool thing with Boolean matrices. You can shortcut stuff based off what we know from propositional logic. So now with everything we know and shortcutted, our resulting matrix looks like this. We'll do one more example. This is, if you're comfortable, you're good. Last example is just going to show this shortcut in greater detail. Let's try that. 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, and then all zeros down here again. All right, nice and short. And then we're going to multiply that by something that has 6 rows, and we'll say 3 columns. Sure, I like that. 1, 1, 1, 1, 1, 1. 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0. Sure. Let's try how to do our multiplication. Well, our resulting matrix, how big is it going to be? It's going to have this many rows and this many columns. So it's going to be a 4 by 3 matrix. 4 by 3. And let's go through that 4 by 3 matrix we're going to end up getting. 4, 5. That's going to be a short 4. It's fine. Let's go through it. What's the color we haven't used yet? We haven't used brown. There we go. It's my favorite color. I'm surprised we haven't used it. Let's start the first. I have said that I know this first row is going to be all zeros. But let's try it out. We have all zeros times all ones. Boolean product. Silly me. 0 and 1 is 0. Or 0 and 1 is 0. Or 0 and 1 is 0. Or 0 is 0, right? We are left with all zeros because these are all zeros. Doesn't matter if this was 1. 0 or 0, we know that's also 0. We end up with all zeros. So 0 or 0, 0, 0 ends up being 0. Oops, I shouldn't have done that. Let's try that with the second column now, right? Second column. 0 or 0 and 0 is 0. Or 0 and 0 is 0. So on and so forth. You can see the pattern. It's going to end up being 0. So if it was 0 for the column of all ones, and it's still 0 for the column of all zeros, does it matter? No. We know by the identity law, right? 0 and P, whatever, whether that's 0 or 1, equals 0. We just showed that. And then we also know that 0 or dot, 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 or 0 is going to end up being 0. If none of it's true, it's going to be false. So this is all zeros. Let's try the next row. The next row has a bunch of 1s in it. Yeah. Weird color. Times a bunch of 1s. What should we automatically assume is going to happen? Just looking at this. Well, we should take a look at this and see, okay, 1 and 1 is 1. Or do we bother going on? 1 and 1 is 1. Or ... Do we even bother with it? Well, what's 1 and P? 1, right? P in this case could be everything past the first item, right? They're all going to be disjuncted together. So 1 or P, where P is literally everything past the first item, if we know one of them is going to be true, the resulting thing is going to be true. It's going to be 1. So we can solve that immediately. 1. I don't need to do that long term. Now what do we have? Okay, 1 and 0 is 0. Or 1 and 0 is 0. Or 0. Or 0. Or 0. Or 0. Now we can see these are all zeros. Okay. So we cannot definitively say if the whole row is 1s, we're guaranteed to get 1s. But we can say that if the whole row is 1s and at least one item here is a 1, we'll end up getting a 1. So let's try this one right here. 1 and 1 is 1. Boom. Or whatever. Doesn't matter. We already got it. Next row. This funky row and the all 1s row. All 1s column. 0 and 1 is 0. And then, or 1 and 1 is 1. Or we found a 1. We're good. We can stop. That's stopping us. We're good. We found a 1. We already know the result is going to be 1. So what can we see here? It looks like if, just like here, if we have a row of all 1s and the column we're multiplying has at least 1 in it, the resulting thing we get is going to be a 1. Likewise, if we have a row of mixed things, a row that has at least 1 in there, times a column that has all 1s, the resulting thing is also going to be a 1. Let's see if the rule holds true here. 0 times that, or 0 times that, or 0. It's a column of zeros. If we have a column of zeros, does it matter what we multiply? What we do and for? No. It's all going to be 0 or 0 or 0. So we also know if we have a column of zeros, everything in that column will also be a 0. So we can skip that step. And looking at our last one, this one we don't have an easy solution for, right? This one we just got to do it the old-fashioned way. 0 or 1 is 0. Sorry, 0 and 1 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 0. Okay, good. We can stop. We found a 1. We're good. Overall thing is a 1. Final row. They're all zeros. What do we know about rows with all zeros in it? Does it matter what we're multiplying? No. 0, 0. Already shortcutting it. This is our resulting matrix. So we can do one more question based off of what we just learned. And let's say we have the following matrix. Yeah, we'll do this. We'll do a nice square matrix for us. 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Let's say this is equal to f. F to the second power is this whole thing times itself, right? So f equals. So let's do the multiplication for that. Copy, paste. So f to the square root of 2, square root to the power of 2 is this. Equals, it's going to be the same dimensions. We know that about square matrices. It's going to be very thin, but it's fine because we're going to shortcut some stuff. Let's start our multiplication. See if we can apply any shortcuts we might know, right? This is going to be a lot of writing if we don't have any shortcuts. Well, before we start writing anything, what can we look at here? Do we have any rows or columns that are all the same? This is a row of all zeros. Since it's a row of all zeros, the corresponding row will have all zeros in it. This is a row of all zeros. The corresponding row will have all zeros in it. This is a row of all zeros. The corresponding row will have all zeros in it. This is we have no column of zeros, so we can't shortcut anything like that. We do have a row of all ones. Maybe that shows us something. Do we want to? Nah, we won't do that approach. And this last one gives us a pause for thought. Is there something we can shorten? Let's find out. Well, can we shortcut any more? First row. This first row has all ones, right? And what do we know is our shortcut? If the column we're multiplying has any ones in it, the resulting thing is a 1. 1. First row. Does this column have any ones in it? Yes, it has one. 1. Does this column have any ones in it? Yes, it does. 1. Does this column have any ones in it? Yes, it does. 1. Does this column have any ones in it? Yes, it does. 1. Look at all that. We remember how long this would take us without shortcuts? You know how long this is? Look what should we shorten it down to. We're down to 1 row left. And let's try that last row. I'm sure this long table, all we're going to have to do is 1 row now. All right, this times this. Okay, now we have to do this old-fashioned way. There's no all ones, there's no all zeros. We can't do any shortcuts. We can look at it and intrinsically be like, okay, this doesn't look very promising. But let's check. 0 times 1 is 0. I'll put it in the middle. It's not like we're using it for anything else. 0 times 1 is 0. Or 0 times 0, say times, 0 and 0 is 0. 0 and 0 is 0. 0 and 0 is 0. 1 and 0 is 0. Great. First one done. Move on to the second one. That's the same thing. That's a shortcut we can see. Didn't we just multiply this row against the column that's identical to it? Yes. So we know this ends up being a 0. This is the exact same, has the same components in it. The next one's also going to be a 0. This one has the same thing. The next one's also going to be a 0. This one has the same thing. This one's also going to be a 0. This one has a different thing in it. Let's take a look at that. 0. So 0 times 1 is 0. So 0 and 1 is 0. 0 and 0, 0. 0 and 0, 0. 0, 0, 0. 1 and 1 is 1. There's a 1 somewhere here. Our resulting thing is 1. So what have we seen? What have we learned from this? Based on what we've just looked at with this specific matrix, with F, we see that f to the second power is that when dealing with a Boolean power. Can we surmise anything from this? Any thoughts? Think for a moment. Think if there's any takeaways we have for it. I'll give you guys some time to think. I'll also take a drink in the meantime. Based on what we have here, is f to the second the same thing as f to the first? Yeah. So what if we did f to the second times f to the second, Boolean product? It's the same thing as f times f. So what would be f to the 100? Think. Well, f to the second is the same. And so to the second times f would get us to the third, which would be the same. To the fourth would be the same. Fifth would be the same. We see a pattern. All about pattern recognition. This is equal to f. We can generalize this specifically for the f matrix, not for all power matrices. This is not the case for all power matrices. This is just for f. This is just for this specific matrix. F to the n is equal to f where n is greater than 0. Because what is f to the 0? F to the 0. Well, actually, that's to the 0 power matrix. Is there an identity binary matrix? I don't know how that works. I would assume so. I would think so. I don't know why there wouldn't be. Yeah, there has to be. So that would probably be just the identity matrix, just except it's now considered a 0-1 matrix. Because the identity matrix is just zeros and ones anyway. So that would probably be the exception. That's why I'm making this rule here. Alrighty. Hopefully this has been a good look at matrices for you guys. Matrices are not intuitive. Right, it's a lot of memorization, specifically the order you do multiplication. I mean, you can hear me struggling to say and or multiplicate or times and plus. Or I switched up those words. I don't know. I have a speaking problem, I guess. But it's not intuitive. It's not strictly an intuitive idea. So, but hopefully, going through this and looking at these examples of matrices and understanding is helpful. One last thing I guess we'll look at. Last question. Is F symmetrical? First question, is it a square matrix? Yes. Second, is the transpose the same? Well, we could bother making a formal transpose, or what could we do? We could draw a line right down the diagonal and see, is everything mirrored? Are these two the same? No, they are not. It is not a symmetrical matrix. All right, just we had the matrix there. We might as well hammer it home. But yeah, hopefully this was helpful. I hope that this was a good look into matrices and a good understanding of just the basics of how matrices work and also 0-1 matrices. Take care, y'all.